Right, in this video, we're going to be discussing Chapter 8, Gases, and the topics that we're going to be covering in this chapter are properties of gases, the first section, 8.1, and then pressure and volume relationship, which is also Boyle's law, called as Boyle's law, and then the temperature volume relationship, that's referred to as Charles' law, and the temperature pressure, which is the Gay-Lussac's law. And then combining all these three laws, Boyle's, Charles, and Gay-Lussac's, the combined gas law. And then the relationship between volumes and moles of gas, Avogadro's law. And the ideal gas law, which combines all of the laws, all right? So all the four laws, okay? And partial pressure, which is Dalton's law, the last section in this chapter. All right, so here you see a respiratory therapist performing some diagnostic test, measuring breathing capacity, concentration of oxygen, carbon dioxide, and the blood pH, etc. Right? So gas laws affect our breathing because breathing is based on Boyle's law, pressure-volume relationship. Lung capacity is affected by temperature, which comes under Charles' law, and so on. So all these gas laws are really important and affect us in our biochemistry as well as our environment. And we look at each of those laws and their applications. So some of the skills that are carried over are solving for equations, sig figs, conversion factors. And now that we learned about molar mass, we are going to be using molar mass and conversion factors based on that. And then, of course, the mole-mole factors, which is a carryover from the last chapter, chapter 7. All right. So we talked about those 7 diatomic gases, which are elements at room temperature, and they are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine. So you have fluorine, bromine, and iodine. All right. So you have those 7 gases that are considered to be elements at room temperature. So there are diatomic molecules, which are gases. There are also, so these are diatomic, all right? They are made of the same element. But they are also other gases made up of different elements, all right? A combination of different elements, all right? So carbon monoxide, carbon dioxide, nitric oxide or nitrogen oxide, all right? Nitrogen monoxide, nitrogen dioxide, sulfur trioxide, and so on, all right? So they are diatomic, they could be polyatomic, they could be gases made up of the same element or different elements, all right? But they all, and the noble gases, which are monoatomic, but they all follow the same type of laws, the same type of properties. All gases are under the conditions that we have, which is the atmospheric pressure, temperature conditions. They all behave exactly the same. They're called as ideal gases. And some of the the theories or the properties attributed to gases come under the premise of the kinetic molecular theory of gases, which explains the behavior of gases. Okay, so we're going to be learning about what this kinetic molecular theory, abbreviated as KMT, is, and then we look at what the units of measurement of gas pressure are. So the the postulates of the kinetic molecular theory is that gas particles are moving very randomly but with high energy, all right, high velocities. They're traveling at great speeds, but kind of random, but always in straight lines. Even though the movements are rapid, it's always in straight lines. It could be up, it could be down, it could be diagonal, vertical, perpendicular, but always in straight lines. And when they are moving, they collide with the walls of the container in which they're contained and with each other. However, those collisions are completely elastic, which means that no energy is lost on impact, right? So generally, if you look at any kind of objects colliding, whether in a bat and ball game, as the bat is coming with a great velocity, as the ball is being pitched at great velocity, at great speeds, and coming and making contact with the bat, all right. Some of it loses its speed as it makes contact with the bat, because the energy from that ball is now transferred into the bat, all right. Now that is very typical of objects when they collide, but gas particles are not like ordinary objects. When they collide, they're not losing any energy whatsoever, all right. All of their energy is always maintained, so the collisions are completely elastic. Also, gas energy is dependent on the temperature of the gas, but in kelvins, all right. So the average kinetic energy of movement of those gas molecules or particles are directly dependent on the temperature. As the temperature goes up, so does the energy. The gas particles start moving even more rapidly, you know. All right, so the collisions on the walls of the container is what is registered as pressure of the gas. All right, so pressure is the force at which those gas particles are making impact per the unit area. All right, so when you go to fill up your car tires, for example, you will see that the units of gas pressure is the PSI, or pounds per square inch. Okay, so pounds is a force, square inch is the area, so that area with which the gas, the air in the tire is hitting the walls of the tire, that's registered as the pressure of the gas. So the properties of the gas are governed by four properties mainly, all right. So that's pressure, volume, temperature, and amount, which is also referred to as moles of gas. So these are the four properties that describe all of the ideal gases. Okay, so we talked about pressure. It's that force by which the gas particles are colliding against the walls of the container. The units of pressure here in the United States and Britain is measured in PSI, but otherwise it's ATM. If you metric is millimeters of mercury and torr. Pascal, kPa, kilopascal, is more the SI unit. And then the volume is that space. Now the space occupied by a gas, the gas particles themselves, very tiny, they occupy very little space. So the space or volume of a gas is essentially the volume of the container. So that's measured in liters or milliliters. Temperature, again, is an important factor because the energy or the motion of the gas particles is directly dependent on that temperature in Kelvin. So in calculations, always convert all temperatures to Kelvin. Otherwise, you get wrong results. All right. Gas temperature can be registered in degrees centigrade, but for calculations must be converted into Kelvin. The moles of gas is usually in moles, but moles can be converted to grams using molar mass. So the units can be both grams and moles for N. So the volume is essentially the volume of the container, because the gas particles themselves occupy very little space. So the total volume of all the gas particles in a container is very negligible compared to the volume of the container. Okay, and now when the temperature increases, if the pressure is constant, of course the volume starts expanding because the gas particles become more energetic. Okay, so the temperature of the gas is related directly to the kinetic energy of the gas molecules. All right, so if temperature goes up, the gas particles become more energetic and there's more collisions. They hit against each other and the walls of the container more vigorously. If the temperature comes down, then there are less collisions because the gas particles kind of become more sluggish. So the collision with the sides of the container, that's pressure, and the units are either millimeters of mercury. Torr and millimeters of mercury can be used interchangeably, or atmospheres. The SI unit is the kPa, kilopascals. So there's another unit called pascals. And then, of course, the American and British system is PSI, pounds per square inch. Okay. So the pressure of gas, we may not think about it consciously, but there is the air pressure that is exerted on everything, all right, whether it's the sky or the surface of the earth. So that air pressure is referred to as the atmospheric pressure, all right. Now 78% of air is made up of nitrogen, 21% oxygen, and then less than 1% is all the other gases like carbon dioxide, etc. So how is pressure of a gas or even air determined? Evangelista Torricelli came up with this ingenious method where he took a long tube, a capillary tube, filled it with liquid mercury, and then upturned it into a dish of liquid mercury. And then what happened was, with the force of gravity, of course, you would expect that mercury to fall down, but that because of the weight of the mercury and the atmospheric pressure acting on the surface of the mercury as a force pushing it, that weight of that mercury that he measured, that was supported by the atmospheric pressure, that was 760 millimeters of mercury. Okay, so 1 atmosphere then was equivalent to the 760 millimeters of mercury, and this is how this was unit was derived. All right, and that because of Torricelli, that's also referred to as 760 torr. Okay, so essentially 1 millimeter of mercury is 1 torr. Okay, they are in a 1-to-1 ratio. All right, so to this day, this is the principle still used in all barometers. Okay. All right, so these are some of the different units of pressure for gases. You have the atmosphere, you have millimeters of mercury, torr, and then inches of mercury, which is not as used, and then 14.7 psi is 1 atmosphere. 101,325 is pascals, but 101.325 kilopascals, and this is the SI unit. All right, so at sea level, it's 1 atmosphere. But above sea level, it varies because it's less dense, the air is less dense. Less particles means less pressure. All right, we'll stop here.